next speaker is going to tell us a little bit more about how communities in the Northeast are handling this variation in our precipitation patterns and a somewhat uncertain future. The Ashokan community is currently blessed with clean water. There is a turbidity problem, but overall the water in our watershed is clean, fishable, and drinkable. But as the climate warms and regions of the world become hot and dry, clean water will become extremely valuable. Water will be life for millions of people. How we respond now to flooding in our communities will help to determine whether our water quality remains high. We're pleased to have our next speaker, Dr. Roy Schiff, join us today. Roy will talk about the lessons of the past and how communities in Vermont, similar to our Catskills communities, are learning to live with streams. Roy is a water resource scientist and engineer with Milone MacBroom Incorporated. He manages MMI's Vermont branch office that he helped open in 2005. Roy received his Ph.D. in aquatic ecosystem studies from the Yale School of Forestry and Environmental Studies in 2005, and his Master's of Science in Civil and Environmental Engineering from the University of Washington in 1996. Roy is a licensed professional engineer in Vermont and frequently works on applied projects including flood protection, channel and floodplain restoration, bank stabilization, and river corridor assessment. Roy regularly gives presentations on flood avoidance and mitigation, where society's needs are balanced with a combination of stream restoration and hard engineering approaches to reduce risks. Roy lives in Montpelier, Vermont, with his lovely wife, 2 adorable daughters, and a sweet dog.
Thanks for that great introduction, which my wife helped write. So I learned something really interesting today. When I leave for work or when I was coming here, my daughter's like, "Bye, Dad," and I said, and they're like, "Oh," they said, "Where are you going?" And I usually say, "I'm going to fishing." And I was like, wow, Bill said, that's an Appalachian thing. I grew up in Virginia. I spent a lot of time fishing in the Shenandoah. It's like, there might be something there. Like, I've never seen Beverly Hillbillies? Right? So it's like, that's pretty cool. This has been really interesting, and I love the Catskills. I've spent a lot of time fishing. When I was young, I met Walt Deddy. He's a Catskill legend, like Art Fleck, and he probably had a big impact. He doesn't know it. He died several years after I met him. He was a legendary fly tyer, and he sat and tied a couple caddisflies for me as I was coming down to the area to fish for one of my first times, and he talked about the river in such a way that it was definitely one of the reasons I decided to spend my life working on rivers. Over the past 20 years, though, it's more work and study and designing projects than fishing, although I'm happy to do a little more fishing with my kids. A couple things from this morning that I'm going to talk about. First of all, there were some great questions talking about the most stable state of rivers, and we're going to address that here, and also about how do you make a recommendation to manage river size infrastructure, and I'll give you some of the ideas we've been thinking about. And one other thing I want to put in your mind as we move forward, I should also apologize, but the last talk I gave was 5 minutes long, and I said, okay, I'm going to limit myself to 10 slides, so 30 seconds a slide, and I'm like, wow, I have an hour today, so it's going to be a barrage of pictures, but I might jump around. Here's what I have in mind. So I was tasked to talk with where we've been for river management and kind of where we're going. So I'll give you some of my experiences over the past 20 years I've been doing this. Talk about corridor protection. That's a place we're going in Vermont pretty strongly. Maybe there's spots we should be backing away from the rivers to reduce our risks and protect some of the features of rivers we all love. Some of the key principles of river management, I'll clue you into those when we get to them. I hope to not only answer some of the questions in the past, but maybe change the way you all look at a river or live next to the river and what it's doing. A couple floodplain restoration case studies, if we have time, that I think are pretty innovative in the region and might be very applicable to the mountainous landscape in the Catskills as it is in the Green Mountains. And finally, to wrap up with 10 ways to improve flood recovery and river management. And this is a project that we've been working on in the state of Vermont, writing new river management guidelines for them. Want to start with acknowledgements. So it's great to be here. Thank you. I want to acknowledge my coworker, Mark, who's in the back there. He runs our New Paltz office and let me stay at his house last night, which was great. And I also want to acknowledge my coworkers, Brian and Jessica, who work in Vermont with me and did some of the work here. And Jim MacBroom, obviously, some of you might know, who's done a lot of work. He's a mentor, colleague, and a dear friend. And then also I should acknowledge Mike Klein. I'm actually a fill-in for him. I'm going to confess right off the bat. Mike's really an innovative river management, leading the Vermont river management program. And a lot of the information and concepts we've done in conjunction with him, and he's pioneered some ways. And I believe there's an article in your packet that Mike and his coworker Barry Cahoon wrote. It's a really interesting article. All right, let's move forward. So here's my picture of token picture of Irene. I love this one. The snow machine bridge is catching all the debris. This picture is taken from Interstate 89. About 2/3 of the valley is cut off by the highway here. So here you see it in full flood during Irene. One of the weird things about Irene was the day after Irene, when the rivers were peaking, was the most beautiful day. It was sort of an amazing juxtaposition. Did anyone see the rainbow driving over here? That was pretty amazing. Sorry. Feel free to ask questions during the talk. You don't have to wait to the end. I was tasked to talk about river management. I kind of found myself changing the title a couple times, and I think what we're going to learn, hopefully from the talk, is all about the river corridors, the area where the river migrates in the landscape, and also the floodplains. The river management is where we often go in to do an action, but it's really a function of what's going on right outside the river, where people have first come into the lands, where people are living, and where a lot of our infrastructure is located. So it leaves us in pinches that we have to manage in the channel, but it's really because of what's going on in the floodplain. So let's move forward. So where have we come from? Anyone seen this slide before? Crooked streams are a menace to life. We've actually come a really long way from the way we used to manage channels. They were a negative thing, and I think probably all of us are here because we really enjoy the important values and economic aspects that rivers provide, fishing and water quality. I mean, these are things that are really important to the soul and to the way we live our life. Yet we still have, go back here. There's a history of armoring rivers, and now we sort of armor rivers in a less negative way, which we'll talk about. So this is kind of where we've been. This is always the favorite, the car revetment. I'm not sure if you want to call that a river, but. And then again, I talk about floodplains, and I want to just show you a couple photos that really just shocked me when I saw them. And here's, any guesses where this is? New Orleans, yeah, you got it. So, amazing just population in New Orleans. All right, this is Katrina. So amazing populations living in flood-prone areas. And, we're managing our rivers, and then we sort of question why some of these things happen. And we're just unleashing, new levees in this area. And also this area has changed the economics of living in floodplains. And we might want to talk about that moving forward. There's been some changes in FEMA policy that really originated from Katrina. There was some neat information from Bill about culture and living in the landscape, and I had the pleasure of working in the Jordan River Valley, and I'm standing here on the West Bank looking at Jordan, and I was never so struck of how much manipulation we have a history of. This is the place where man first walked, first planted a seed, birth of Christ. There's so much cultural significance in this spot, yet you're in a militarized floodplain that people rely on for their food and for what little water is left. So I think it's helpful to step out of a temperate region where we're dealing with floods and recovery and think about some of the other aspects that the world faces. This is not a Catskill region, issue or a Green Mountain issue. It's really a world issue in terms of how we manage our rivers and floodplains. So there's a history here, but here's current day. Vermont Fish and Wildlife did an assessment of the amount of dredging that went on the rivers after Irene, 77 miles. In Vermont, we have a lot of geomorphic data, the study of the shape and size of river and how it's changing. We'll talk more about some of the principles of geomorphology that I think are really important for us all to know. What we found was, of those 77 miles straightened, in those watersheds, 176 miles of river had historically already been straightened. We are caught in a management cycle, conflicts and management that are impacting our water quality and the way we live in our floodplains. Bill mentioned the word migratory. Populations that were migratory that came into our floodplains and along our rivers. We're not migratory anymore. We've hardened a lot of our river corridors and floodplains, and so we get trapped, and that's where we have these conflicts. They lead to excessive downcutting that we were just talking about, right? So that process is natural, but when you change the shape of the corridor and floodplain, you change that process. I'm going to talk more about that. In '76, there was a big flood in Vermont, and the state did a really qualitative assessment. Did we leave ourselves in a better or worse spot? None of the work that they did in the rivers left us in a better place in '76. During Irene, 20% of the work. This means that we might not, if the river eroded it out, we might have not filled all the way back in, so things were back in risk. Okay, so in '76, 60% of the work done was estimated to be putting us in a more vulnerable or risky spot in terms of risk to infrastructure and people, water quality impacts, habitat impacts. This time we did a little better, 40%, but that's not a great statistic that in that many years we're still leaving our streams in a pretty rough shape when we have a flood like this. And we just learned it was an extremely rare event. So these unfortunately are not pictures from the past. These are pictures from the past couple years. Here's a shot in Vermont. Here's a shot on Stony Clove. All right. So we're caught in these management cycles. One thing I want to try to show you is that we know this spot's depositional. We know it now. I don't know when we actually learned that there was low stream power or the ability to move sediment, and that this bridge, like much of our highway infrastructure, lands where the river flattens out. That's where you got to put stuff. That's where people are living. So we happen to land in a lot of the most vulnerable spots across the landscape. And this is really magnified in a mountainous landscape like we all are around. So let's talk about dredging. I'm sure it's going to come up, so I'm going to jump the gun here. You dig out a hole in the river, right, and you make capacity. Now, when that bridge was closed off, there aren't many options. Another flood comes, there's nowhere for the water to go except downtown. But there are places where we might be able to not dredge, and these are the reasons you don't want to. One of the first ones is you create this nick point, right? You can't dredge, or it's not cost effective, and it's huge impacts to water quality and habitat to dredge a whole river, so you dredge a piece of it in the profile looking downstream. And that destabilizes the area. So that dredged area will migrate upstream. If there's people and infrastructure, the banks will become unstable, the river channel will cut down excessively. So you can initiate a whole process that destabilizes a much larger area. A major tenet of river management now has to be we cannot increase risks to other people when we do a single action in the river. Here's another slide that Jim MacBroom made. Rivers go through natural trajectories, and we're going to talk a little bit about this. They do cut down in the landscape, like the gentleman over here said, but they also preferentially sort their material. And for those in the back who can't see this, it's hard to see like from here down, right? Yeah. Okay, I'll try to describe that. The bottom slide shows boulders and coarser material aren't naturally armoring the bottom of the bed. Rivers tend to create, especially in mountainous landscapes where there's coarser material, they tend to create these natural cobble beds and armored beds of boulders, right? And think about what happens when a flood comes, more sediment goes on, we get the machine in there and we start digging. If you cut through this layer, you are initiating a process that will change the river's course for a very long time on the geology scale of it. Right? This natural armor layer is a critical aspect of what we do in our rivers. We always need to know where it is vertically and make sure people working in the rivers know. So I just want to throw that out there with the dredging. So in the bottom right, we were making our rivers and our riverscapes very rigid historically. We got to get water, get stuff in the river, and get it out of our way. And then people were saying, well, there's so many water quality impacts with that. It's not a river. We want the habitat there. And people started to do projects like you see in the upper left. This is another project. This is a project that Jim did early on in his career where he said, why can't we design a river that looks like a river? Right? God forbid we didn't make a trapezoidal concrete channel as a floodway, but we made a bankful channel, a floodplain or flood bench that might mimic what's out there on the landscape, and then terraces like Danielle was saying, and even in a built landscape. So this is a concept. Now, this river cannot migrate very far. It's in a very built environment. So this may be a village setting river, but maybe there are places where we can let rivers go, and we're going to talk a little bit more about that. River management and infrastructure design was all about water for a long time, and now we know it's really all about sediment and debris. Okay, so when we change woody debris, we're affecting the stability of many kinds of channels. Small mountain streams rely on wood for their stability. Clearly, they have huge roles in habitat, and so areas where trout fishing is essential, wood can make up half of the base of the aquatic food web, so wood is essential to leave in your streams. And sediment goes one-in-one with the stability of a river channel. So anytime we change the sediment, whether we dump a big load in if a mountain fails in a flood or we start digging it out after a flood, we are really changing the course of the river and the stability of it. You saw a picture of Stony Clove earlier. As we looked into the design of that, and it's a really, really spectacular landscape there, we looked at some of the history of the river. You don't need to see the slides in the bottom for those of you in the back. It just shows the individual lines. But what I wanted to show you is we know rivers move across the landscape. That's what they do. They erode, they deposit, and they migrate. And they migrate in a known area. Okay, this is a really important concept. That area has been termed the river corridor. Some people call it the meander belt width. So if you essentially went down the river and drew lines outside the meander bends, that's the most likely spot you're going to find the river over the long term. And you can see there's a road here, so that impacted it. But if this stuff wasn't here, it would migrate across the bottom of the valley. That's how the valley was formed by the river. So we have the bankful channel, your low flow channel, and then that river corridor. And you can see here's an example of an old channel. It had cut down. And then you have your floodplains. So you have sort of two management areas, that river corridor and that floodplain. And here's another shot of it. These red lines show the mapped river corridor. In a little bit, I'm going to go through a process and show you how in Vermont we're identifying these areas and using them to help manage our rivers. And this is another shot of a river that's been migrating across the landscape for nearly 100 years. And it's a case study that I like to tell you about because I went in there with my engineer hat on and my rod and level, and I walked out of there with a conservation project because it was unfeasible to stabilize this bank. You can see the sediment loading. There's a huge sediment source upstream of this river, and the slope breaks here. You can see the sediment bars building. See these rocks here? This farmer told me that one winter when there was a thaw in January, he used a sled and dragged over boulders and rip-wrapped this bank, and this is where that bank was located. So this is the first year he did it, then about 15 years later here, then it was here, and now it's way out here. So the material is very erodible, and when it sloughs and the river gets up, it just pulls away. And so you really can't armor this bank effectively in this spot. Here's an example of some of the mass inputs. These areas exist all over the Catskills and all over a lot of our mountain terrain. And this is the problem. There's an undersized bridge that's not letting the sediment out the door. So we could go in there and armor and invest loads and loads of money, but we're really not going to change the scenario in this spot. So the idea was, go back to here, was to back out in this spot and let the river play its course. The sinuous patterns land in a predictable area on the landscape. We just heard a great talk on hydrology. It was really informative and interesting. And here's my recommendation as a person who has to sort of come up with some design flow. Matt Collins out of NOAA made this plot, and it says exactly what Alan just said. The gauges around, this is the northeast region, are all showing increased flood flows. So this is an analysis of the gauge, and the size of the triangle shows the rate of increase. And I was hoping someone had something in New York, and you covered that perfectly. So when Matt found this out, he made a recommendation to stream restoration people that he saw a big change in the flow patterns around the 1970s. And what he recommended was that we should be looking at a range of flows. We can't put our blinders on and say the Q50 or the 50-year flood should be the design flow for a culvert. We need to look at sort of a bracket. And one of the ways he said to do that was to split your flow record if you have a long flow record, calculate your normal gauge statistics, so the 100-year flood or the flood that has a 1% chance occurring each year for the whole record, and then break it at 1970 and look at the old record and look at the new record. And we've been doing this around the region during our work, and we're seeing there's huge changes. There's like a 20% increase when you just use the more modern gauge record. Yesterday, I took a minute and did this for Stony Clove, and an example, I saw that the 10-year flood, if you just used the more current half of the gauge record, was 1,000 cubic feet per second larger. So, one thing you might want to do is calculate your design flow for the whole gauge record, and then look at, if you have a long-term record, look at the more modern half of the flow. This has huge implications for design work and managing our rivers. I'm going to jump over that. And here's the reason why. So rivers migrate across the landscape. They go from headlands to ocean, and they carry water, sediment, debris, ice, and anything else that gets in their way during floods. And they do it in a balance with sediment and flow. So sediment input from the watershed and flow input from the watershed. And then there's resistance. Then there's the material in the bed. And then there's stream power. I'll talk more on power, but again, power is the ability of the stream to do work. And this is really the slope of the channel and the flow in the channel. And so there's a balance here. So all rivers out there are working to this balance, and the way they do that is they adjust their size and shape, and they adjust their curvature. Okay, so flows are increasing. Okay, let's pull this side of the scale down. This arrow goes that way, and we get degradation. You just saw a picture of degradation, the excessive downcutting of the river. Now, what I've seen is this scale really teeters back and forth. Sometimes you're in degradation, and sometimes you get aggradation, and that's equilibrium. You have not an excessive change. But then when you get changes in the corridor and floodplain, your flows can't get out on their floodplain. The river starts to cut down, and you can imagine that now you're squishing all your flow down. Now when those increased flows come, you're stuck in the river more because we're in the way with infrastructure, or the river has already cut down away from its floodplain, and now you get more and more degradation. So the answer to the question is, yes, rivers do this naturally, but no, they don't do it at the scale we see because we've transformed the floodplains and river corridors that they migrate through. Okay, and you can see this, I love driving through the Catskill towns, levee, wall, riprap, floodplain. And it's nice to sort of try to, pick out those areas where the river can express itself, not be as erosional, let go of some of its energy and material, and then kind of go through the villages in that confined setting. I think here we have to walk a balance of, can we get the water through certain spots and let it spread out certain spots, both for water quality, habitat, and for risk reduction. So this is a key concept, the equilibrium balance of streams. I mentioned stream power. Sorry, the slide's a little small. I got to get one equation in there, the engineering side. Gamma is the weight of water, Q is flow, and S is slope. Okay, so let's think about that for a second. Let's get some discussion on here. So where in a watershed might power be the highest? Any guesses? Let's just do upper, middle, or lower. Anyone got a guess? If it depends on flow and S, someone said it, I yell out. Middle, right? I always without thinking, I was like, oh, high power, steep slopes, right? That's where it comes out. But really, it's sort of these middle order streams, third and fourth order. That means you can't jump across them, but you don't have to swim across them. You can wade across them. So the combination of Q, the watershed input, and S are the highest. When you get way at a bottom, at a lowland river, there's no slope. The power goes down. When you're way up high, there's not enough flow. So somewhere in the middle. And what this graph shows, this is from a group out of Australia. This shows low energy, medium energy, and high energy areas and stream power. So different size and shapes of rivers based on different power, different positions in the valley and landscape. We can understand what our risks are and what the river should look like in a certain setting, and then really understand the conflicts and how we need to manage these rivers. Here's a nice diagram by Nansen and Croak. In '92, they wrote this paper talking about different kinds of floodplains. Steep mountain floodplains are high energy, and they get a little higher energy once they widen out and pick up material. And this is what it looks like following Irene. This is a small stream you could get across in 2 hops, this is Route 4. Barry said, let's go check out a washout. I'm thinking about a culvert. Turns out it was 3 miles of a major state highway. This is a teeny stream in a high power setting. So here's your medium energy floodplains. Okay, this is a braided system. We see a lot of these around the Catskills when the streams lose some slope and spread out their material, and then they come back in a more confined setting. Right. Here's a medium energy braided system in Bennington, Vermont. For scale, you can see a giant. This is one of the biggest bulldozers I've ever seen. 10-foot wall mounds of sediment, just phenomenal sediment movement during this event, in addition to the flooding. And we'll talk about that a little bit more. And then some low energy type floodplains. So if we know what kind of floodplain that should be in the valley setting, we sort of know our risks. This is an example of that. Low energy floodplain. You can see here, this is a real interesting, I'm going to talk about a project here. This is a raised rail bed that cuts off this area of the river. Going back to Stony Clove, so let's think about that balance. We have higher flows. We have a road that comes down the mountain. We have a road that's confining these areas. And these dark areas, this is a difference between 2 elevation maps from LiDAR. And the darker the red, the more the loss of material. Okay, so you can see that there's been a lot of erosion in some of these bend areas as the river is cutting down. The river's cutting down in all these channel spots and trying to migrate through to regain its equilibrium. That's why Stony Clove is moving. It's trying to get back that slope and balance. Part of it is the history of industrial works that have gone on, some of the filling incrementally for housing, and then ultimately around 214. That's confined this in the valley, and part of it's the geology here. So Stony Clove would naturally be doing this, but now it's locked in here and trying to get that energy in balance, and it's got to cut down and widen out. My favorite Greek philosopher is Heraclitus, and he said you can never step in a river twice. Think about that for a second. So fishermen probably know this really well. Every time it rains, you're just like, where'd that hole go, or where'd that bar go? Rivers are constantly evolving in their dynamic. And I think our early river management did not acknowledge that. And I think now we're moving to a place where it's primary into how we think about rivers. This is a really important concept, and I hope will forever change the way you see a river. Rivers go through evolutionary stages, typically over geologic times, but when a flood comes, a river runs through a lot of these very quickly. Floods are devastating, and it was Irene and Lee and all the others in 2011 were tragic, but as a river scientist, it was incredibly educational to see some of this play out overnight. And so rivers start, you can see they're connected to their floodplains. Then they cut down, as this gentleman said, and then they widen out. Okay, and then they actually, as that material comes down, they fill a little bit and reconnect old floodplains. Okay. Now, this is known trajectory for every river, and there's going to be no test on this one. And those in the back, don't worry about what you're not seeing. It all looks the same. But the point is that all rivers cut down and all rivers widen out, and then they'll kind of build up a little bit and re-go through the cycle. Okay, so we can't, I don't want to say have the arrogance, but we can't have the misconception that we can block off rivers permanently in many locations. So how does this play into the ground? This is a pretty phenomenal data set. There are 26,000 miles of rivers in Vermont of all orders, and 2,000 miles of those have been walked by someone in geomorphic assessment. And I think this area is incredibly well studied as well. And this is the evolutionary stage we just talked about. So 1 and 2 are beginning, 1 is stable, 2 is starting to cut down, 3 is really cutting down, and 4 you're widening out, and 5 is returning to stability. What these data say is that 3/4 of our streams are cutting down and widening in their evolutionary track in Vermont. So assuming this is representative, that means one of every 4 streams is stable. Right, so having an understanding of this is really essential part of how when we collect data to start work on all the streams in the region. This little house figure, unfortunately the people in the back can't see it, but what if you arrive to a site, let's say the first peoples came over, were migratory, and then all of a sudden, the rivers, let's say, were at a certain place in the landscape in stage 3, and then everyone came, and the tanneries and the shacks and the cart paths that turned into asphalt roads. And now we're in stage 3, and our infrastructure and our society is sitting in those areas. And these are the conflict spots that we all know about. They're all over our country and our world. And then we armor the river, and we've just made a commitment, a financial commitment for life or generations at least, until something changes, whether the river, the inputs in the watershed may change due to some of the changes we just heard about, or possibly a change in how we recover from the next flood and move back. But if the trajectory, if we know a channel's in stage 3 and we're in the floodplain and we're armoring, it's a long-term commitment financially, and the risk will remain in most cases. And here's an exact example of that. This one really caught my attention. New home construction. I mean, look at this bank. This is just shocking. And when you see these sediment bars, you all may know that these are some of the most dynamic areas when the river dumps its material and then rolls off and starts moving across and trying to rebalance its equilibrium in these spots. Sometimes the more confined settings feel like they're a little more stable, and then this is where it all plays out.
What's wrong with removing gravel bars like that, where if you don't go below your base, that's the armor?
If you remove this gravel bar, you likely will initiate a incision that's going to run out of this depositional area, and the bed will cut down. The other thing is this gravel bar. This is on the eastern slopes of Mount Mansfield. This is a high bed load stream, and it's sitting on glaciolacustran material, a very fine material from when there was a glacial lake here. So if that cuts down and gets into that material, which it will have a better chance of with this stream will again change its trajectory into a really complicated thing to manage, and that has happened in some of these spots. The other thing is the mechanisms that deposited this bar are going to stay right here. So this bar might be pushing the channel to migrate a little bit, and that might be a cause where you say maybe we should get rid of that bar and get the river going straight. This is right downstream of that, so where some management has taken place, and then this is right downstream of that where you have an undersized bridge. So the whole setting of the conflict with your And the point of this slide was that this armor is exactly in conflict where the river's going. And so then what you get is a 13-foot hole under this bridge. You can really initiate a process of erosion that goes beyond the risk of what you have already. That's probably, in that spot, I'd unrecommend it. I mean, there are spots we're going to have to manage right when water comes out. The bridge in Phoenicia is a spot where we're there, and until there's a change in the mechanism or the setting, it's going to be a management flashpoint. I mean, the bridge will close off unless the material gets through. I acknowledge that and appreciate that because there are a lot of people's lives down in the floodplains where we all live. At the same time, I acknowledge there are areas where we should not be encroaching on the river, trying to manage everything. Let's see. So I want to change gears a little bit here and talk about this river corridor management. And this is something that's taking place more and more, even in the engineer's toolbox in Vermont, which you might find a little surprising. You don't need a scale or a slide rule for this one. I just gave it away. Maybe that was good. So this is on the edge of the 100-year floodplain. And this is the result. And the water never inundated this house. And our state spends a lot of money, as does New York, on flood recovery. And one of the reasons is erosion hazards. In mountainous landscapes, erosion probably does just as much, if not more, damage than inundation hazards. So thinking of all these geomorphic principles, and that says, how much space does a river need to become stable at the end of the evolutionary process? Mike made this slide. Wherever this river is, how much space does it need to become stable? And you can see here, this is showing how, here's your valley bottom, and here's a small development, and the river's pushed off to the side. And so there's this whole process of doing geomorphic assessment, collecting data, do it remotely, and then in focal areas go in the field. And this mimics a lot of the work taking place in New York. And then doing what's called river corridor planning, establishing those river corridors where the river's most likely to be, and developing projects, whether they are river management projects in conflict areas or conservation projects outside of those immediate conflict areas where we can let the river do its thing and try to reduce our risks and impacts. Okay? This rings like the buffer philosophy where you took the river and you drew a line, all right? But the problem was the river moved. Right, so now the idea is the dotted line shows the meander belt. Right? We go out and we measure the amplitude of the meandering, and we put a line there, and then sometimes you put a little extra line if it's a very dynamic site. Okay, and there's been a lot of research on this topic to know how wide that meander belt needs to be based on the geomorphic stream type. And then once you know that, you know if you're in a low, moderate, high, or very high or extreme sensitivity rating based on the geomorphic stream type. And then that dictates how many channel widths you should be away from that channel. And that's the most likely spot, where the river is going to migrate. Okay, so identifying these risk areas. So we have our inundation maps, which we're all familiar with, the floodplains. And then we have the erosion maps where the river might be migrating in its future. The two are related, but they're different. In Vermont, there's actually a move to have towns adopt this into their zoning. They make a commitment to trying to promote backing away from the river. Properties in there now are grandfathered, but they're trying to limit people going into these river corridor areas. You can imagine there's probably some contention about this approach, but as a whole, 22 communities have chosen on their own to adopt it. I will tell you that I've witnessed some of these hearings when towns are debating whether to do this, and there's no pressure by the state to do this. People say, if you want to do it, that's fine, and if you don't, that's fine. So it's really come from the community level. I actually have a suspicion, the way our stream alteration rules are going, that this might become a statewide concept, but that's just a hunch. I have no information to support that. Wanted to talk to you about floodplains for a second, and then talk about a couple projects. FEMA in 2013 contracted a study by a group called Earth Economics out of Tacoma, Washington, and they looked at the economic values of floodplains. Now, I am not an economist, but I spent a lot of time tinkering and thinking about floodplains. The results of the study said that for things like aesthetics, air quality, biological control, erosion control, flood hazard reduction, that riparian areas are worth $37,500 per acre per year. Okay? That comes down to $12.30 per square foot. The reason this study was done was the true benefits of floodplains were not getting factored into the FEMA benefit and cost analysis procedure. So if I had a flood risk and I damaged a house, I get the value of the house and I compare that to what I'm proposing to do and see if it's financially viable. And now, this is now a part of FEMA, not the most progressive agency. That FEMA says that $37,400 per acre is the value of a functioning floodplain because of these risk reductions. This is, I think, an important step moving forward. This is that study I referred to that said they found that $32 million up to $433 million was the cost of functioning floodplains in Pierce County, Washington. And these data, how they value the functions of the floodplains, again, which is sort of beyond what I'm comfortable talking about, went into these figures. So functioning floodplains are not only important to reduce risks, protect water quality, they have a huge economic value. And we're going to be working on a study that takes this to a local level in Willsboro, New York, and Waterbury, Vermont, balancing the costs and benefits of different floodplain development scenarios. So I have a couple case studies now in about 15 minutes. I think what I'd like to do is run through one of these, and then I'll let you all choose how we wrap up. This is the Roaring Branch in Bennington, Vermont. This is really the history of Bennington, Vermont. It's a small town that has regular flood damage. And this picture is from the 1890s when massive areas of the town are destroyed from sedimentation. That says, "Prepare to meet thy God." Little post-flood graffiti. Here's 1980s, massive river deposition. Here's it after Irene. There are pushed up berms all over the land. There's one of our few Army Corps levees. You guys have a couple of. This is it, functioning. The Army Corps levee had a clay interior, and clay interiors and high power streams don't go well together. They do great in the Mississippi when your water comes up and slows down, but they liquidate and dissolve. So the clay, I suspect some of the levees around here have clay cores, and hopefully they don't get undermined. The river cut down 10 feet next to this one and just undermined the levee system. And there are homes all around this, so big flood hazard area. Bridges clogged up, so we had to empty out the bridges. 500,000 cubic yards were delivered to a 1 mile stretch of river during Irene. That's 12 to 15 yards per dump truck, 500,000. Pretty astonishing. The source of sediment in our mountainous landscape is pretty much endless. So we can just count on dealing with material coming into where we live. Here's a model. I'm going to jump through this. This is just showing the profile of the river, elevation on the vertical scale, and distance, showing the sedimentation thicknesses as they played out after Irene. This is what that bridge looked like. I walked under that bridge several years ago in early 2000s. There was about 10 feet of clearance. And after Irene, I crawled under it on my belly to get to the other side. And here's the issue. Bennington sits in an alluvial fan-like area at the base of a mountain. If you walk across Bennington, you'll see flood channels and coarse material all across the village. The river right now it says 200 feet wide in this spot. We were going to widen it out to 300 feet, and I'll show you why. But the real width of the river it was 2 miles. The river would come down and change course historically. Here's an example of that. These blue lines show old river paths in woods a mile away from the river. So looking at the picture, you can see here's the Army Corps levee. Here's the river flowing this way. And then here's pushed up berms in yellow. And the idea was we're going to push these back to the edge of that river corridor. Right? The study showed that this will buy us a little bit of space. And by taking out the berms along the river, and because there's industry and houses here, we had to push it back. So it's essentially putting a berm further back on the floodplain. And the question really probably in all your minds is that going to do anything after it's not 2 miles. This is the take-home slide, so see if you can follow this. So vertical axis is channel change, the elevation of channel change. So essentially sedimentation. If you see a spike, there's a big pile of sediment after the flood. And we're looking down the river. And what you see is, under existing conditions, in front of the Park Street Bridge, there's a 4-foot aggradation. Okay, pretty close to what we saw during Irene. It's a little low, actually. First alternative, let's dig it out. Right? We dig it out, and lo and behold, nothing has changed. The process of delivering that sediment is still there, and the big flood comes, and the spike, the bridge is clogged again. It's a $1 million+ structure. When we connect those floodplains back in the middle, you see more sedimentation that's spread out over that extra 400 feet, and the sediment deposition at the bridge goes away. Does everyone follow that? So you can dig out the river, but the big pile of sediment's coming back. But if we change the mechanism, we give the river space to spread out and distribute that sediment in a spot that's not as risky as this location, we can avoid the danger on the infrastructure. Here's a quick photo synopsis. If you keep your eye on the machines in the back here. Okay, so this is one phase of it there. And you can see there, and it extends back up in here. And again, the only reason these berms are here is because there's infrastructure and properties on the back there. So we essentially took spoil piles and fill and pushed them back a few hundred feet. Irene came and finished the job for us. That was phase 1, and this was phase 3, 4, and 5, courtesy of Mother Nature. But the thing was, this plan was in place, although it wasn't ready for construction. And during flood recovery, we just recovered on the back of the floodplain. So we just sort of used nature. So I guess it was really important to have the project ready, even though it didn't all get constructed and we were working through it in piecemeal. Because then when we had to do something quick, and the reason there was some sediment removal done here is the sediment filled to the top of the levee in this whole area. This was part of that 500,000. So Irene finished it. So I have 2 options. One more floodplain project. We have 10 minutes, or I could talk about the top 10, kind of what we're doing in Vermont on flood recovery and river management. Do you have a question or a vote?
Question. You were talking.
Or we can just do questions.
You were talking about the economic value of floodplain.
Oh boy.
How do you build that into, say, incentives for developers not to build there? How do you recapture that economic value?
Good question. I think one of the ideas is that you have to sort of do a cost benefit for people. These studies really just looked at one side. What is the benefit, right? And I mentioned that study. I can go a little further. What we're going to look at is where people are in the floodplain, the value of those buildings, how much it costs to restore those buildings when they're damaged, and then what are the benefits from the natural system we're losing to improve water quality and maintain habitat and so on. So until you do a full accounting, you don't have that information. I think that's one of the ideas behind the origin of this study we're working on. I haven't done a lot of research on the topic to know right now how you could portray that message, but it has to be a full accounting of, there is the theory out there that if I say don't build in the floodplain, it's loss of economic development. And I appreciate Bill's comments this morning that these people landed there because their ancestors took them and their descendants took them to these floodplain spots. Now, I don't think it's, well, I guess finish my thought is they're landing in really dangerous areas for themselves and for our society. And so I don't think it's only their responsibility to sort of, sorry, this is where we gotta like, this is where it all has to play out and you lose. It's the state or the country's got to say, we need to migrate away from these zones to keep the landscape safer. And so I think there has to be just a complete picture. The benefit side was really never talked about. It was always like, I'm losing my house or I'm losing my building or the economic prosperity of a downtown area. So I think you just have to have a complete accounting, and not a great answer, but. So any thoughts? One more case example of a floodplain project or the top 10? Top 10. You know? Okay.
Was Bennington spared the effects of Irene? Was
well, the village itself, for the first time in one of their big floods, didn't get nailed. I think it was really because the way the rainfall played out. I don't want to take credit. Half of this project, a third of the project was built. I think the project probably helped save the bridge. It started to get damaged, but the waters were spreading out, so no definitive. I don't like to. Yeah. I won't show you the other floodplain project, but we took out this rail bed. I showed you one piece, and this is a map of sediment. We did a quick quality, evaluation of it. And then what we did was we looked at how much sediment was deposited on the floodplain once we reconnected them. And the answer was we reconnected for this project 200 acres of floodplain. And we documented 1,400 cubic yards of fine sediment splayed on just 3 of the many floodplains we worked on. And there was 1 metric ton of phosphorus on those sediments. So there are huge water quality ramifications for connected floodplains to catch material. And here's an example of one. You can see the floodplain here, and there used to be a 8-foot-tall rail embankment. This was really a circumstance where someone said, oh, this rail line's getting taken out. We can just lower the embankment and reconnect the floodplains. Okay, so top 10 in 5 minutes. So back to, oh, it's the exact same scenario as last time. This is the 5-minute talk. All right, so I get 1 sentence per slide. One of the keys after our flood recovery, people went at the rivers with the dynamite. We really need to have an on-the-ground alternatives analysis to do the right thing. Someone's got to look at the river and know about the trajectory, so we're not still 40% more risky. And this really helps controlling the costs and minimizing the future risks. The damages we see are actually a function of a river process. A highway engineer said safety is about the size of the road. Well, your safety is really about the type of river you're working next to. So if you see a road wash out, you need to know if the river's rapidly incising during flood. So linking the damages to the channel condition to the processes. Thinking about scale, and I think there was a question about how much down cutting. If we see areas that are rapidly cutting down and then we go in and rapidly fill or rapidly remove material, we need to think about how things play out over time and over space. A little too much detail to get into, but there's bar growth and then there's meander dynamics and the river moving up and down. And so positioning your project, when a flood comes, the scale is shaken because we're seeing things happen that should be happening over centuries happen over hours. So that's an important consideration. Follow best practices of geomorphology and current engineering. Simple things. Don't take out the armor layer. Don't cherry pick every coarse particle from the bed and stick it on the bank. Don't cut your rivers too deep. These are things that are just well-known ways to manage river. Rebuild coarse things in the river and bed forms. Restore your reference geometry. We often build back to the exact dimension pre-flood where you don't need to sometimes. If landowners are willing to be okay with a loss of 20 feet, armor their bank further back. It's going to make a big difference in risk reduction in the future. So And we talked about power versus resistance. That's an important aspect. What power setting are you in and what's the resistance in the banks? Restore your floodplains, and this is a project you just saw. We learned about managing towards this equilibrium. This is the fundamental concept that's essential to create a least erosive, vertically stable state. Okay, so if we confine and reconfine following floods or dig heavily, we will get those excessive erosion spots over and over again that destabilize the banks. But if we can back away in spots, we might be able to let off some of the pressure. Dredge only where infrastructure and buildings are vulnerable. Vermont governor got up there and said, do what you got to do. All permits are off. Do what you got to do to recover. And there was a field day. There were people dredging in the pucker brush. Like, there was nothing around. People were just hogging out the river, both for material, but mostly it was like pent up energy of years of not being able to dredge. It's like, we're going to get the river back. Properly size your bridge and structures. Use a range of design flows. Vermont's moving to the 1 times bank full width minimum. There's a whole host of other aspects. Maintain. We look at the geomorphic compatibility of a structure. How well does a structure fit? If I were to design that bridge down in Phoenicia again, it'd be a lot wider because I know sediment's coming down in there. It needs spot to store sediment in that spot. And then maintain aquatic organism passage. And last but not least, conserve river corridors to provide the space. If we do a good job at this, this is really the way we're going to move forward. We need to sort of migrate out of these most vulnerable spots. One thing I haven't said explicitly is the habitat, that we all enjoy fishing and whatnot, is really formed and maintained by these processes. So as they play out naturally, our streams get more productive and healthy. So it's really risk reduction, habitat, water quality. Thank you very much. 3 minutes.
We have time for like 1 or 2 questions. So if somebody wants to ask, and now maybe during lunch you could maybe grab Roy.
So if a community had the resources and liberty to rebuild a bridge in a different location, are you suggesting that it be in a steeper grade area? Would a steeper grade avoid some of the problems that you've been describing? That is a steeper grade of the river.
Thinking that it might be a more confined setting, a transport setting. That's a possibility. I guess what I would say is that when we site our infrastructure, keeping a lot of the principles I just mentioned in mind, we can pick spots that reduce risk. A lot of times those sites are not accessible for a move because something's there or whatever. But I think a natural narrow spot is a place we historically have put bridges and dams for probably convenience and for reduced construction effort and all that. But there might be something said for putting a structure in a steeper location where you think sediment transport is taking place rather than these deposition spots. Unfortunately, our historical patterns have put some of our biggest infrastructure at these breaks in slope, especially in a very undulating terrain. So that is an option. And so what I would do is sort of really understand my geophysical setting to find the spots. Maybe there's a constriction in the valley that is transport, or maybe a little steeper spot. So I think it's something certainly to consider. And don't just go for the sort of flat spot where the excavator can sit the most comfortable and build the widest abutment. We got to look at the river stuff.
We often go back to the same spot in the stream and fix things over and over again. Can you speak briefly about the long-term costs and benefits of looking at the whole stream corridor from one end to the other as opposed to just addressing the problem spots?
Sure. I think it's almost impossible to understand what's going on at a project site if you don't know the larger context. I'll say that, and early on, I'm guilty as anyone going to the spot and really trying to fix the problem. This is in conflict with every agency of transportation in our country, they don't even have the right to go outside of your structure. For example, let's just take a structure. And so it's complicated, but you have to go outside and understand this setting. And let me take an example. If I find I'm in a low power setting, sediment transport's not taking place, and I'm right downstream of a high power setting, wherever I site a structure, if it really needs to be super wide, might retain sediment in that location. But I need to know that there's a lot of material coming down. So you really need to sort of have a context to place a project on the ground. If we're managing sites over and over again, it's certainly an invitation to sort of step back and understand the broader context. Now, if there may be local opportunities, like the rail bed was like an obvious local opportunity, like circumstances just aligned that we could take that rail bed down, and then we kind of knew that we just need deposition area based on the river setting. So it's really a combination of both, but I really think you have to start at that broad scale, really understand what setting you're in, what does the valley want to do, and then drill down to what do I want to put around the river, or what's around there, where can I move back, and sort of create a big picture. I mean, there's a reason it's a corridor plan and not a site plan. A site plan's for a house, a corridor plan's for managing those events that influence a village or a neighborhood or a community. It's a bigger scale that's really essential to think about. It's a great point, though. I mean, it's really important.
Thank you, Roy.
All right, sure. Happy to talk at lunch.